Welcome everybody to the second unit of the first week in the Parallel Programming Concept course in OpenHBI. My name is Peter Tröger. So in this unit we want to talk about Moore's law and the power wall problem, which is very prominent today in parallel processing hardware. So let's have a look into how processors work. If you take a modern computer, then the architecture of the processor and the computer itself follows common principles that are known from computer architecture. The most prominently and most widely used concept here is the so-called von Neumann architecture. The von Neumann architecture was invented around 1945 as part of larger computing system projects. And the idea here, the new idea at this time, was to build a processor in a way that you treat the instructions, the code, the software to be executed as data. So the code, the software itself lives beside the data to be computed in the same memory. This was a novel idea then, because before we had only systems with fixed programs that were burned into or built into the hardware and were not exchangeable. With the von Neumann architecture, we were now able to exchange the code to run different programs on the same piece of hardware in order to have a flexible machine for different tasks. The basic building blocks in the von Neumann architecture are the control unit and the arithmetic logical unit. They both together form the central processing unit, the CPU, or what we typically call a processor today. Beside this, we have some kind of system bus, which is in newer systems exchanged by an interconnection network. And this system bus now connects the main memory, the RAM, and input and output devices with the CPU in order to get an overall computer system. This is a very simplified structure, but it shows you some of the most relevant details we have with the processing of programs and instructions. So whenever the CPU wants to execute a particular instruction, it has to get the instruction from the memory, it has to get some piece of data from the same memory, and then it can perform an actual computation or any other kind of operation. One of the most relevant trends that we have in such processor technology and hardware is the so-called Moore's law. Most people already heard about that, and the original statement by Gordon Moore, one of the Intel founders, was that the number of transistors that can be inexpensively placed on an integrated circuit is increasing exponentially. So this is a law that basically talks about hardware developments, improvements in the building of processor technology, and the message here is that for costs that are acceptable, you're able to double the amount of transistors in one processor die or in one processor chip every 2 years. So if you double the amount of transistors every 2 years, you get an exponential growth in the number of transistors. This is an interesting aspect because all these transistors are actually used to build the hardware parts that form the processor itself, like inbuilt memory, like the registers or caches, logical gates for the actual computation. And all these transistors now enable the hardware vendors to deliver new capabilities with the processor technology. And the Moore's law, after a while, turned out to be a self-fulfilling prophecy. So companies such as Intel really try to fulfill this promise to double the amount of transistors by improving their production capabilities and other things, and to get better processors every 2 years. From time to time you will find in the literature misinterpretations of Moore's law claiming that the performance of a processor doubles every 2 years, which is not exactly right, as we will see in the following slides. So Moore's law basically only talks about improvements in hardware developments. And recent research and recent analysis attempts figured out that this law still may hold for the next 10 to 20 years, and then we will reach ultimate physical limits and need completely new approaches for processor technology. Moore's law's effect can be seen by trend charts and development charts like this, where you can see that on the y-axis we have a logarithmic scale for the number of transistors per processor chip, and on the x-axis we have the time And you can see there that there's a constantly increasing number of transistors on all these different processor generations, regardless of the vendor. So this Moore's law is valid, was valid for decades, and gives us constantly improving capabilities for processor hardware. So what about software? If we now have the situation that processor technology gets better and better and delivers you more capabilities, maybe for performance, the question is this really useful for software? And there's an interesting talk in the internet, we will give it to you in the optional readings, and this was Nathan P. Myhrvold talking about the next 50 years of software in 1997. And he made a very good quote about the problem where he said, software is a gas. It expands to fit the container it is in. And the message here is, whatever the hardware industry is delivering as a new capability and a new kind of computer technology that you can use for your software, software will find a way to use it. Software is a gas. Software will find a way to use all the available hardware resources, regardless of how fast or how good they are, in order to deliver better services in back-end services, or to deliver better experience for desktop computer systems. So whatever hardware people deliver, software people will use it. Software grows until it becomes limited by Moore's law. That was another quote. So the growth of software never ends. This is a trend we saw for the last decades, and it still holds. Yeah, so whenever software people get new hardware being available, they will find ways to exploit it, to get some interesting application out of it, so that new user services can be delivered. Software grow is actually also something that makes Moore's law possible and plausible. So we have the situation here that the software development and the hardware industry constantly stimulate each other. So whenever hardware industry delivers a new piece of capability, software people will use it, and will use it in a way that the hardware gets exhausted and there is a need for a new generation of hardware. There are also other people making the same investigation, like you can find in Jevons paradox, that says technological progress that increases the efficiency with which a resource is used tends to increase the rate of consumption of that resource. So whenever you give new resources, hardware resources, computational resources to the users, they will find ways to use it, to exploit it. And this was a trend that held for many, many decades, since in the 70s and 80s, computing became a common thing for most people. And around 2000, we got an interesting effect with all this exponential growth of the number of transistors and the according improved performance of hardware components. When you look on different developments and curves, like the number of transistors versus the clock speed and the power consumption, you see that clock speed, power, and the performance per clock cycle started to get capped around 2000. So after the year 2000, we got a trend that frequencies of processors no longer increased. We got a trend that the power consumption somehow was stalled, and that several indicators of fresh and new hardware developments that make software transparently faster no longer increased. And the question is now, why did that happen? What was the problem there? Herb Sutter made this investigation in 2009 with a famous paper he published, and he described all the effects we still see today, that although Moore's law is still delivering an increasing number of transistors, we see no longer an automatic effect on the performance of software. So the question is now, why did that happen? What is the problem here? And in order to discuss that, we need to have a short dive into physics and need to see how hardware behaves and how does that impact the software itself. So when you talk about processor technology and processor hardware, you first talk about power consumption. So a processor needs power in order to perform its work. Power is therefore the energy that you need to run the processor. And this power consumption can be distinguished into two parts. There's the static power on the one side, and this static power is the leakage from the transistors while they're inactive. This is a well-known physical effect. You can't avoid it completely, and this is something you have to put into the equation for the power consumption of a processor. The second thing is the so-called dynamic power, and this is the energy you need in order to switch the transistor, for example, to implement a logic gate functionality that ultimately implements calculation capabilities or other capabilities of the processor. And this dynamic power can now be approximately computed. This is not an exact formula, but approximately computed by taking the number of transistors you have and the capacitance, the average capacitance per transistor, multiply them. You multiply that by the voltage you have to the square, to the power of 2, and the frequency. So you have this formula where the dynamic power consists of several parts, and whenever one of these parts, number of transistors, voltage, frequency, increases, then the dynamic power consumption increases. Moore's law now gives us the situation that the number of transistors you have to consider for the power consumption of a processor is constantly increasing. So we have given from Moore's law, we have an increase in the power consumption, which needs to be considered, because somehow you must deal with all this power, since this power more or less completely gets dissipated from the hardware, and you have to take care of this by the terms of cooling. So power dissipation that comes from a processor, from all the tasks that are fulfilled, now needs to be covered by cooling mechanisms. And the cooling mechanisms have to deal with a particular power density, which is sometimes measured as watts per square centimeter. So your processor delivers heat due to its power consumption and the work it's doing in the static and the dynamic power consumption part, and this heat must be got away from the processor in order to avoid that it failed completely due to overheating. So how can you deal with that problem? The historical approach to deal with the dynamic power increase that comes from Moore's law is to bring down the voltage. Why this? Because voltage is used in the formula, in the dynamic formula, to the power of 2. So if you decrease the voltage for the processor, you actually can reduce the energy consumption quadratically, which is a really huge impact. So this was an easy approach to deal with the larger amount of transistors and their power needs by just reducing the voltage step by step with each processor generation. The second idea is to use the increased number of transistors not only for logic gates and their switching needs in the dynamic power formula, but to use it, for example, for larger caches. And by using such tricks and methods, hardware industry was able to deliver us, before the year 2000, constantly new processor models with increased frequencies and an increased number of transistors. So you got more performance from the mechanisms implemented by the additional amount of transistors, and we got additional performance by the increased frequency. One example you can see in this chart, where the power supply over the years is shown. This is a slide also from Gordon Moore, and you can see that while the frequency constantly increased, we had a constantly decrease of the power supply of the voltage, also again with a logarithmic scale, and meanwhile we are near 1 volt of power usage for processor technology. The problem, although, was that even with the usage of these trends and tricks, we got into the situation that the power density, the amount of heat that was dissipated from the processor, still increased. It wasn't as heavy as it should have been with the exponential growth of the number of transistors, but it still increased. And you can see on this chart that after 2000, we started to go into the area of power density where it became really, really hard to deal with all that heat and to get it away from the processor die. So with 120 watts, which is some kind of power density we can find in modern processors, you're really close to the air cooling limit. So the problem is you have higher temperatures in the hardware, which again leads to increased leakage in the transistors. Those transistors get slower, so that's a bad effect, but you also get to some kind of limit. So how does that look in practice? Here's a nice example from practice where some guy on the internet was able to bake an egg on his processor by just removing the cooling. So we really have a lot of heat that has to be removed from the processor surface in order to make it operable. Okay, the second problem was that with the increased temperature in the processor die, we had an increased amount of leakage in the transistors. And this leads to the fact that power leakage, static power consumption, becomes an increasing problem, which adds to the overall power equation. So you no longer have only to deal with the dynamic power needs, but you also have an increasing amount of static power consumption that by the processor simply from Moore's law and the trend that you have more and more transistors on the chip. Okay, so all these effects in sum can be now described as the so-called power wall. So the power wall is an effect in processor hardware that basically claims that air cooling capabilities or cooling capabilities in general are limited. You may use modern approaches such as water cooling, but they're also capped in their capabilities. So you have a problem with getting rid of all the heat that is produced by the exponentially increasing number of transistors, and you have to deal with the power consumption problem. The power consumption increases as long as Moore's law continues to deliver new transistors, but on the other hand, you have to promise, or at least to fulfill the promise of constantly increasing hardware performance. So we get the problem that although we have more transistors, the power wall problem hinders us in using old-fashioned approaches of delivering better processor performance. You may say, okay, then let's reduce the voltage again. This worked quite well for the last decade, so this may be another option. But since we are already close to the physical limits, we start to get strange physical effects in the processor hardware, so reducing voltage is also no longer an option. So we're now facing the situation that the next and upper next generation of processor hardware needs to consume not more power, but even less power in order to deal with the increasing transistor count. How can you do that? There are a couple of proposals how to do that. The first one is to lower the frequencies. Yeah. So if you lower the frequency or you keep it at the same level, you may be able to deal with your power consumption problem. Another approach that can be found in modern processor technologies, such as in the processors from Intel, is dynamic frequency scaling, where you actually have not a constant high frequency, but you adapt the frequency according to the particular needs of the computation at this point in time. A second way of dealing with the problem is to use only parts of the processor at a time in order to avoid the overall overheating of all the processor surface. This is an effect called dark silicon. You can find additional information in the readings. And the problem here is to deal with that on the software side. So how can you still deliver faster software with additional hardware capabilities while you're not allowed to use all the processor transistors at a time? And the third idea of dealing with the power wall problem is to build special purpose hardware, to no longer build general purpose processors, but to build things like GPUs or inbuilt special capabilities in the processor, for example, for encryption or text processing, that allow you to solve the same computational problem faster, but with less hardware components. Okay. So the overall message of the power wall problem and Moore's law is that we had a great time with hardware development until the 2000s. We had constantly increasing processor frequencies. We constantly had better capabilities inside the processor. But this has stopped due to problems with heat dissipation, with cooling, with power supply. We are now in the situation that we can no longer rely on the hardware people to give us faster processors that automatically make our software run faster. So since 2000, the software people, the software industry is now in the need of using modern processor technology explicitly in order to get faster software. And this is a big paradigm shift to what we had before.